So this is the form of collective communication when you are trying to split and send the data from different processes to everybody else. And as you can see, it is not very straightforward to set that up. So the MPI library already have a set of collective communication routine to enable you on how to do that. The one thing about collective communication routine is that all processes within the scope of a communicator have to call that routine. And if any single process fails, basically what, for example, looking at the previous code, let's say if one of the process fails, there will be another process with an MPI receipt hanging. So if one process fails, that will mess up the entire set of collective communication. So you basically have three types of collective communication on synchronization. Everybody wait until everyone reaches a certain point within the code. Data movement, you want to broadcast data, you want to scatter the data, you want to gather the data. And you want to do collective computation. You want to collect data from everyone else and perform an operation on that data. And you want the other participating processes to perform somewhat of a partial operation on that data. So this is the visual explanation of the collective communications. For broadcast, one process send the same data set out to everyone else. For scatter, you are trying to do the same thing, but basically you have a huge chunk of data, you divide it into individual workloads and you spread out the processes. Gather is the reverse of scatter. You have data, you want to bring it back and put it together into a data structure like an array. And reduction, you have data, you want to bring them together and perform an aggregation operation on this. So it is very simple, the syntax for this. On collective communication on broadcast, you need to call broadcast the data you want to send out and the root processes where you want to send the data. Everybody should call the same thing. And the operation is different on different processes. On process 0, the data variable actually contains the data to be sent out to the others. And on any processes that are not process 0, the data variable is where the value from process 0 going to be written into. That's what broadcast looks like in C code. This is what it looks like. Let's say you have process 1 with 7 after you call broadcast. You have 7 across all other processes. MPI reduce, again you have the data. So for MPI reduce, all processes should have that data value. The op, that means the MPI operations, and you can call MPI min, MPI max, MPI sum, MPI product, and there are other MPI operations that you can run. And root is where you want the final value to be written into. The MPI reduce code for C is a little bit different because it has the send buffer and receive buffer. I believe the MPI reduce for Python is you set the final value equal to some variable. So with that, go ahead and redo the previous exercise, but this time you don't have to. Make sure that the processes talk to one another, but to use MPI broadcast and MPI reduce to send out the data and to gather the data to each processes. So this is what the reduce function should look like. Reduce. So you need to have the send buffer, and you have the receive buffer. The receive buffer on anyone that is not a root process doesn't do anything, but the receive buffer on the root process is going to store the final value from the operation into that buffer. Yes, sorry? Sorry, can you say?
Do we need the same buffer in reduce?
Yes.
What is it?
So, okay, let's go ahead and start to do an example. So let's say my temp is my rank. So I can call com reduce. Let me look at the syntax. Oh. Okay, yeah. So the syntax of the reduce is, so for this reduce, for the lower case reduce, you don't need the send buffer and receive buffer. You need the send buffer, and the receive buffer is actually a value that you can assign to. So for com.reduce, the syntax that I show in here, this is actually correct, and the return value of this syntax is going to be that aggregation. So sum comma reduce. So in this case, I print out the value, the sum variable for everyone, but only value 0, only process 0 has the value here. So you can see from this. Process 1, 2, 3, the sum is none. It has not been initialized yet. And only process 0 has the final sum is 6. Because that was the root process in the MPI reduction code.
What if we say the root is equal to rank?
No, the root in this case I set root equal to 0. So you have to specify that. You cannot set the root equal to rank because that means for individual processes, it's going to have different root target. So this command has to be the same across all processes.
You have to get the return value broadcast as well. In order to do the broadcast, you still have to get the return value from that broadcast.
You can broadcast nothing and you receive nothing. So
Right, but there'll still some will still be uninitialized and everything except process here.
yeah. So initially all the sum is equal to 0, but because I set sum equal to that and the ML reduce call from any process that is any non-zero process doesn't return anything, the sum is set to point to 0.
Right.
But then after I do that, I should have the sum value set of everyone set to 6.
I think you still have to get the return value.
Oh, you mean this? You're correct. Thank you.
And then why does it say none instead of 0? If you initialize it to be 0, then why does it say none?
Oh, I initialize it to 0, but I messed that up when I do this.
Oh, interesting.
So it will not be 0. So let's say if I do this,
So do you have
if I do if rank equal to 0, then I call this function this way. Else.
But the whole point is that you don't have to do that, right?
So if I don't do that, sometimes you might want to be very customized regarding your processes, and you want to make sure that they, even with it work, for example, in reduce, I can have 4 processes doing 4 different operations, and the variable name might be different. So in that case, a list of if would help with that.